Alright, in the last video here, we're going to talk about what we think of as quote-unquote the normal chain rule, because our previous definition just really was a higher dimension case of our one variable chain rule. And what you end up seeing is if you Google chain, like multivariable chain rule or whatever, you're going to get some different things popping up, and so we want you to be ready for that too if you ever do decide to Google, say, Paul's online math notes. And so here we want to begin with an analogy of climbing a mountain. Okay, so if you can imagine, a mountain climber has a path up a mountain. It might zig, it might zag, and do all sorts of wonky stuff, go around the other side, da 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 da, and then eventually the climber will make his way to the very top. Woohoo! And so here's the climber. He's very happy, and he's saying yay. Okay, but the idea here is that if you were to think of his path on the mountain up to the mountain top, we could overlay a grid. And so I have a grid here in black. And again, you would do this with a computer to make it more precise and everything. And so we have a grid. And what we can think of is that at a particular point, oops, I want to do that in other green. Okay, so you have a point x, y, okay, and for a given point we can find the climber's height, okay, and so on and so forth, okay. So what we're saying is that the function fy is representing the climber's height, and x is the GPS location. Okay, but really there's some other information going on in the background. X and y are actually functions of a couple other things, right? So typically, your height isn't just going to be determined by two things, but if we look at kind of altitude by map coordinates, right, these are actually going to be functions of, say, t, which is time, and maybe, things that could affect your height at a certain time or your position along a path might also be s, which we might say wind speed, right? So if it's really windy, you're probably going to go slower versus if there's not a lot of wind, you might be able to go faster, okay? So really the punchline here, f is ultimately a function of s and t, right? So I'm kind of curious, f of s and f of t, or f sub s and f sub t, so the partial derivatives of f with respect to these two, what are they, right? Okay, well, as we saw in the last example, we could find it in one of two ways, right? We could say, first, we could, substitute s and t into x and y, or into f of xy. Okay, so that's kind of that second method, right? Like, you do the composition, you're done. But really, the method that we're going to focus on is chain rule. Because why not? Okay, so what I see is that I have this new function. Let's call it h for the composite function. So I have h of st, right? And we're saying that this is f of, and then this function, I'm just going to give it a name, p of st, okay, which is the same as f circle, or f composed with p of st, okay, and again, just a reminder of the context here. So f is the height, p is what we would have in our x position due to s and t, so wind speed and time, and then similarly for y. Okay, so then according to the chain rule, what do we have? We have that, well, d of h, okay, of st is equal to, all right, df of p of s and t times d of p and then s and t. Okay, and then now just expanding this a little bit, let's see what's all in here. So this would be the partial of h with respect to s, and this would be the partial of h with respect to t. And then what do I get here? This is going to be, well, this really is just del f del x, and then this will be del f del y, and then here this is where I get a 2x2 matrix, which should be del x del s del y del s. Oh, I'm sorry. Try that again. This should be del x del t, and then here we have the y's, so del y del s, and this is del y del t, okay. And so then what I get is, if I do the matrix multiplication, I get, let's just call this hs and ht. This is going to be, okay, and I'm going to write it out using partial notation, del f del x, and then del x del s, and then plus del f del y, and then del y del s. Okay, and that'll be the first entry, and you get something similar for the second entry. Okay, and if we, well, let's just write it out. In shorthand notation, it'll be f sub x, and then x sub t, and then plus f sub y, and then y sub t. Okay, and then from here you can just equate the entries. So just to highlight this stuff, the h of s should be this whole first component, and then h of t should be this entire second component. Okay, so I imagine one question you have is, Professor Bright, why do we have del f del x and del f del y in here? Okay, well, remember at this point still that x and y are still placeholders, so we would differentiate f leaving the inside alone, right? So we would differentiate f, and the insides are still x and y, so we can still use that. So technically it should be del f and then p of s and t. I agree completely, but again, we're just leaving those x and y's there as placeholders. Okay, the x and y really change out when we get to that second component. Okay, So that's where this general notation comes from. And so really, if you had many more parts, it would just be del f del x, and then del x del s, and then del f del y, and then del y del s, and then you do del f del z, and then del z del something, okay? You would just, or del s, right? So all the components, this is just essentially saying all the components for s are included here, and then all the components for t are included in this second part. Okay. Now, one thing that students like to do is they say, "Oh, well, right, Professor Bright, there's x's there, so I can cancel those." No, 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 no. This is very intentional. The notation here is specific, so we can't cancel these out. These represent different quantities, so you cannot cancel. Okay, but instead, at this point, to hopefully prevent students from canceling out the notation here, the books have a tendency of creating tree diagrams, right? So they're saying for a function z that is f of x, y, if it's being composed with, say, s and t, okay, so they're saying that they're looking at f of g of s and t, okay, and they're doing it this way. So they're saying, all right, well, if we want the z derivative with respect to s, that's going to be the function component in x with respect to s, and the function in the y component with respect to s. So what we would see is that, well, we want to end up with all the branches of the tree that terminate in s. So in a tree diagram, we would first have to take del z del x, okay, which they're using f instead of z, okay, just to help you keep the notation separate, and then multiply that by del x del z, or del x del s. And similarly, for the second component, you would have to take del z del y, and again, they're changing z to f, just for notation purposes to keep them different, and then del y del s, okay? And that would be how you get that one. For the second one, you would then do del z del x del t, and del z del y del t, okay? So for both those branches. Okay, so that's the chain rule from a larger perspective, and if you were to visualize it differently, that will conclude our videos for this week.